Hello, hope you guys are enjoying your e-learning day today. So before we get started on decomposition reactions, I just wanted to remind you to upload your synthesis and combustion worksheet from yesterday to today's Schoology page as a PDF. And then after we do the notes here, your homework is to do the decomposition worksheet, and you can either print it off and turn it in on Friday as a piece of paper, or you'll be able to upload it as a PDF to Friday's assignment page. And if you have any questions, give me an email. So today we're going to be looking at decomposition reactions, and we have a few more of those than we had in synthesis. But if you remember, decomposition is pretty much the opposite of synthesis reactions, so you're going to see some similarities in the decomposition that we talked about yesterday in class. But with all decomposition reactions, we usually need some sort of catalyst to get the reaction going. And when it gives you a catalyst, we do not include that as a reactant or a product. It is put on the yield sign, the arrow, because even though it is needed to get the reaction going, it is not used up like the reactants are. So we put it on the yield. So our first decomposition reaction is, this may look familiar, it's kind of the opposite of that second synthesis reaction that we talked about yesterday in your notes. And this is where we take a metallic hydroxide and decompose it to form a metallic oxide and water. So again, if you just flip that second synthesis reaction around, you have this first decomposition reaction. Remember, anytime we're dealing with a metal in a compound, we have to crisscross charges because that'll be an ionic compound. So an example of a metallic hydroxide decomposing would be manganese 1 hydroxide. Now here the catalyst is the heat. So oftentimes you'll see heated, or we could have electricity, or like you saw in the types of reaction activity, the hydrogen peroxide was decomposed using a compound, manganese dioxide. So the heat is actually considered our catalyst in this situation. So if we take the manganese hydroxide and write out that reaction, we end up with MnOH, since manganese is +1 from the Roman numeral and hydroxide is -1. And then it's going to break down into the metallic oxide. So again, we have to crisscross our charges, with manganese being +1 and oxygen being -2. That gives us Mn2O, and then water. And then to balance it, we put a 2 out in front here. And again, in terms of showing the catalyst, I really don't care unless it specifically tells you to include the catalyst. But what you may see is a little triangle. That is what we represent heat with. So heat is represented on the yield with a triangle. But again, you don't have to worry about doing that unless it specifically tells you to include the catalyst. So that's our first decomposition reaction. The next one also should look familiar to you from yesterday's notes. If we take that third synthesis reaction and flip it around, we've got this next decomposition reaction where we take an acid, and when it's heated, again, the heat is the catalyst, it's going to form a non-metallic oxide and water. So again, we're just flipping around that third synthesis reaction from yesterday. So here we have sulfuric acid decomposes. So what that looks like, if I can pull it up, here we go, maybe, is, so sulfuric acid is H2SO4. Now, just like we saw in the that third synthesis reaction from yesterday, where we just combine the non-metallic oxide and water together to make the acid. Here we can just take the water out of the acid, and so I just took the two H's and one of the O's out to make the water, and then what's remaining is the sulfur, in this case the sulfur and 3 oxygens, to give us sulfur trioxide for our product. So I find it easier with these reactions to write the water first and then base the non-metallic oxide on whatever's left over after we take the water out of the acid to form our non-metallic oxide. And again, there's no crisscrossing charges with that because the non-metallic oxides are molecular compounds, and those should already balance since we're just separating out the acid into the water and the non-metallic oxide. So you won't see a whole lot of those. Now the next one is a very particular type of compound. It's a metallic carbonate, and so when we heat a metallic carbonate, it's going to form a metallic oxide and carbon dioxide gas. Okay, now we formed a metallic oxide up here with the first decomposition reaction, and so we're also going to form a metallic oxide with this decomposition reaction, but this one is also forming carbon dioxide gas. So an example of this would be sodium carbonate. So that's our metallic carbonate, and it says it's being heated. So when sodium carbonate is heated, it's going to break down into a metallic oxide and carbon dioxide gas. So it will look like this, where we have oops, sorry, pushed the wrong button. So we have sodium carbonate, which is because of the crisscrossing, sodium's +1, carbonate is CO3 -2, so we crisscross the 2 down here. And then our metallic oxide, again we have to crisscross the charges with our metal, so we have Na2O, because sodium again is +1, oxygen's -2, and then carbon dioxide, so that's CO2. Now you don't have to put this, but I included the up arrow in case you see that from time to time, and that's just telling us that we formed a gas, carbon dioxide gas, so we can put an up arrow, but again you don't have to do that unless it tells you to. And again, the catalyst here is being heated, so if you want you can put a triangle on the yield sign to show that it was heated, but again, unless it tells you specifically to do that, you don't have to do that if you don't want to. Now in this case, this happens to already be balanced, but that is not always the case. So again, anytime we're dealing with ionic compounds, make sure you check your balancing. So these will not necessarily already balance, so always go back and make sure everything balances up. Okay, our next decomposition reaction is a metallic chlorate. When heated, will form a metallic chloride and oxygen gas. So again, think of your polyatomic ions, metallic chlorate, that's ClO3-, and again, because it has a metal in it, it's ionic, so we have to crisscross our charges. So if we have calcium chlorate being heated, it's going to form a metallic chloride, which again we'll need to crisscross charges, and then oxygen gas. So that looks like this. So calcium chlorate, since calcium's +2 and chlorate's -1, we get CaClO3 And then again, if you want to put the little triangle for heat, you can, but you don't have to, on the yield sign. And then our metallic chloride will be calcium chloride, CaCl2, because again, calcium's +2 and chlorine's -1. And then remember, oxygen by itself is diatomic, so we have O2. And then in this case, we do need to balance it. Our calciums and chlorines are already balanced, but since we have 6 oxygens on the reactant side, need to put a 3 here to make 6 oxygens on the product side. And again, here's an up arrow just to show you that oxygen's a gas, but you don't have to worry about that unless it tells you to include the up arrows. Our next decomposition reaction is where we have a metallic oxide forming just a metal and oxygen gas. So it's basically just breaking down this metallic oxide into its individual elements, which happens to be a metal and oxygen. So like iron 3 oxide when it's heated. So that's our metallic oxide. And then that will separate into the metal and oxygen gas. So iron 3 oxide is Fe2O3, because again we have to crisscross our charges. Iron's +3 with oxygen's -2. And so then we just separate it out into the individual metal, iron, which is not diatomic, it's just Fe, plain old Fe. But oxygen again is diatomic, and I included the up arrow. Again, you don't have to worry about that, and you don't have, I'll put the yield sign on here, but you don't have to worry about that either. And then we need to make sure it's balanced. So since we have a 2 here and a 3 here, we need a 2 out in front to make 4 irons. Put a 4 here, and then 6 oxygens. So again, this basically just separates the metallic oxide into its individual elements, which is also what this final decomposition reaction does. So these last two are both very similar to that first synthesis reaction. So this last decomposition reaction is just any type of ionic compound, a binary. Remember, we talked about this back in October, whenever we first started naming ionic compounds. Binary ionic compounds are just a metal, non-metal, just 2 elements. So this last decomposition reaction says any binary ionic compound can decompose into its individual elements. So again, really technically, number 9 and 10 here are basically like the synthesis 1. And again, the less you have to try and memorize, the better. So if you can think of these as just the opposite of synthesis 1, and then like I said up here, this reaction number 5, this is basically like that second synthesis reaction. So it's just the opposite of synthesis 2. And then this number 6 reaction, this is the opposite of synthesis 3. So instead of trying to memorize all these different reactions, if you just know you flip these synthesis ones around and you get these decomposition, that gives you a few less things you have to try and memorize. So here we're just splitting any binary ionic compound into its individual elements. And I think this might be the same one we did for the synthesis 1. Potassium nitride going under electrolysis, so that's another form of a catalyst we can use to make a decomposition reaction work, is to run electricity through it. So potassium nitride, again, we have to crisscross charges since we're dealing with an ionic compound, so that K3N, because nitrogen is -3, and then we just split it into its individual elements of potassium. And then nitrogen, again, is one of our diatomics. So once it's by itself over here, we need to make it a diatomic. And then to balance it, we need a 2 out in front and a 6 for the potassium. Now, if you want to show the electrolysis on the yield sign, you can put a little ELE, or sometimes it might even show like a little lightning bolt on there. But again, unless it tells you to include the catalyst, you don't need to worry about that. And again, like you saw with the hydrogen peroxide in the types of reactions activity. The other, if we have a compound as a catalyst, like the manganese dioxide, we put that on the arrow again as well. So it's not considered a reactant or a product. It goes any catalyst, whether it's heat, electricity, or some type of compound, we put those on the arrow. Okay, so again, just pay close attention to what substances you're starting with, and to determine what type of substances it's going to form. And again, anytime you're dealing with the metal, you've got to crisscross charges, and then once you get the skeleton equations written out, make sure you balance it. And you're welcome to label, is it decomposition 5 or 7 or whatever. I'm not going to check that when I grade it. I'm just going to look at your products and make sure everything's balanced correctly. Okay, so again, make sure you submit the synthesis and combustion worksheet to this Schoology page before the end of the school day today, and then either print out the decomposition worksheet to turn in on paper Friday, or you can do it on Notability and upload it to Friday's Schoology page after we go over any questions you may have. All right, well, have a good rest of your day, and I will see you on Friday.